Okay, guys. Hello to everyone. Uh, I come from Poland, from Kielce city. I work for the Kielce University of Technology. The Kielce city is just localized on a halfway between Warsaw and Krakow. So from Kielce, you have halfway everywhere in Poland. I would like to talk to you about friction in Bioliquid, which is similar to blood. And presentation how I should switch this by point. Okay, thank you. The agenda is following. The first of all, I will say about objective of my studies and also about motivation of this research. Next, I will tell you a little bit about methods of measurements of solid liquid flows and also about nature of this kind of flow. Next, it would be methods of mathematical modeling, short description. And later on, I am going to tell you about some analogy between solid particles of kaolin clay and red blood cells in human blood. And next, I would present physical and mathematical model of bioliquid flow. As I will show you validation of rheological model as well, and some results of simulations and conclusions. So the objective, as I mentioned before, I would tell you about friction, importance of solid concentration on friction in bioliquid, which is similar to blood. So I chosen bioliquid with concentration of red blood cells from 46% up to 70%. The motivation of these studies is that there are no data in literature about influence of high solid concentration of red blood cells on friction. So this kind of research is also important if we consider mechanical or chemical additives which affect on the blood flow rate. So methods of measurements. Generally, we recognize two methods of measurements. There are intrusive or non-intrusive. Intrusive, there are some examples like thermoanemometry or probes. And if we talk about non-intrusive method, we mainly recognize particle image velocimetry, ultrasound measurements, also tomography and magnetic resonance. And magnetic resonance is most popular in case of measurements of blood flow. And also there is positron emission particle tracking methods as well. So this figure is most important to understand nature of solid liquid flow. The red line shows how the friction depends on the flow rate. On the OY axis, there is pressure drop or wall shear stress, whatever, because there is strict relation between pressure drop and the wall shear stress. And on the horizontal axis, there is a speed flow like bulk velocity or flow rate. So as I mentioned, the red line shows results of the friction for the water. When we consider two-phase flow with density of solid particles higher than the density of water, we see other curve, and this curve looks differently comparing to water. From point 1 to point 2, there is a flow which possesses stationary bed. It means that solid particles sediment on the bottom of the pipeline, and they still stay in the same position, and flow is above those particles. Between 2 and 3, we can recognize moving bed. It means that some particles settle down, however, they are slowly moving in the flow direction. And later there is asymmetrical flow. It means that majority of solid particles is flowing at the bottom part of the pipeline, and rest of particles is going up. And the symmetry flow is beyond number 4. It means that all particles are uniformly distributed across the flow. So these figures I mentioned to you is very important because the presence of solid particles in the carrier liquid can increase turbulence or decrease turbulence. This phenomenon is extremely difficult to understand and to measure. And in some cases, we are looking for depressing of turbulence, while in some cases in engineering, we are looking to increase turbulence. I will give you some examples. We know that the fastest runner on 100 meters is Usain Bolt. I'm not quite sure is it he still champion world championship, but his velocity is 37.5 kilometers per hour. But if we compare how fast can swim dolphin, we know that dolphin can reach 50 kilometers per hour easily. But look at on the carrier liquid. There is air for world championship because he is just running in the air. Air has density about 1,000 lower compared to sea, and viscosity of air is also about 1,000 lower comparing to sea. However, dolphin can swim faster. How it's possible? There are some theories why is that, but roughly speaking, this is dolphin knows how to use his how to swim to decrease swirls, to decrease turbulence around him. So this is his just nature. So we see that turbulence is very important in engineering, and here is some example how presence of solid particles affect the flow. At the OY axis, there is pressure drop per 1 meter, and on the horizontal axis, there is a bulk velocity of solid liquid flow. And we see at the bottom there are lines appropriate for water, but if we consider solid liquid flow with average density about 1,667 kilograms per cubic meter, and if we assume that this solid liquid flow is non-Newtonian, we see that cylinders show experimental data. But if we would like to use CFD modeling and predict such kind of flow, we see that empty squares shows results of predictions. So predictions are much higher that it should be. Why is that? So on the base of this, we can assume there exists a suppression of turbulence in such kind of flow. So we recognize in some cases suppression of turbulence in the flow, while in other cases we can face that there is generation of turbulence during the flow caused by presence of solid particles. Several researchers try to develop formula. Is it suppression or is it generation of turbulence? But unfortunately, until now, there is no simple formula because the problem is complicated and depends mainly on the flow conditions. So if we consider methods of mathematical modeling, roughly we can divide them on direct numerical simulation when we use Navier-Stokes equation and we solve the problem directly from Navier-Stokes equations. This, of course, requires long time computations, and also nodal points must be located very, very small to each other. Distance is very small to each other. So it's complicated and it is not very practical from engineering point of view. More practical seems to be large eddy simulations, which has got good results in many predictions. There is also artificial neural network of machine learning, but we know this is a box that we put something inside and we get results, but we don't know exactly what happens, what is phenomena of this flow. And there is a modeling of turbulence, which use random average Navier-Stokes equations, which is more practical for engineers because we are talking about average in time velocity, not just random velocity, which is not useful for engineers. So in this case, I will use random average Navier-Stokes equations. Let's talk about physical and mathematical model of this kind of flow. So I assume that this is Bioliquid. I don't call this exactly blood because there are some assumptions. So this Bioliquid is similar to blood, but this is not exactly the blood. We know that we face problems in measuring blood velocity distribution, especially in vivo. Because you know that veins are moving still, and we are not sure what is the exact position from the wall. So, from this reason, these kind of measurements are not very exact. What happened is that some researchers found that results of measurements of wall shear stress are lower comparing to predictions. So some researchers noted that red blood cells are moving from the wall to the symmetry axis, causing that there is a layer at the wall free of solid particles. So this could be the reason why wall shear stress at the wall is lower comparing to measurements. So if we consider blood, we know there are major components. The most important is plasma. Plasma, this is carrier liquid. And majority of plasma, more than 90%, contains water. And the rest of stuff, this is some ions, some nutritions, and some few components, not important from flow point of view. And there are also platelets, which are responsible for flocking. And there are also red blood cells. Major solid particles in the blood are just red blood cells. They can possess 30 few percent of concentration, and sometimes even 70% of concentration. This depends on many factors. Is the human sick or not? Is it, for instance, running or having exercises or not, etc. So, concluding, we can say that blood can be treated as a liquid, which is treated as a carrier liquid, and as a solid particles, which are red blood cells. So I just found some analogy between blood and some liquids which exist in engineering. I am talking right now about kaolin suspension. Kaolin suspension is a special suspension with very small size of particles. Size of particles is usually few microns, about 3, 4, 5 microns. While we consider erythrocytes, it means red blood cells, they have dimension from 4 up to 7 microns. So dimension of solid particles in kaolin suspension and red blood cells are quite similar. Shape of solid particles and shape of erythrocytes seems to be also a little bit similar, because erythrocytes, they are usually thin discs, and they are similar to solid particles in kaolin. There are, of course, some differences. For instance, red blood cells are flexible, while solid particles in kaolin are not flexible, they are rigid. Solid particles possess density about 2,400 kilograms per cubic meter, while density of erythrocytes is about 1,060 kilograms per cubic meters. However, if we consider suppression of turbulence, we know that suppression of turbulence exists in slurries, it means solid liquid flows, which possess solid particles with high density, and also in case when solid particles density is low, not much higher than water density. So if we consider carrier liquid, so in kaolin, the carrier liquid, this is pure water, while in blood, this is plasma, which, as I mentioned before, possesses more than 90% of water. So let's talk about physical model. What I assumed in my simulations. So I assumed that solid particles in suspension are fine with diameter of few microns. And I assumed that suspension is non-Newtonian, what is true in case of kaolin suspension, what is also true in case of blood suspension. Blood is non-Newtonian liquid as well. I assumed that carrier liquid is water, and the flow is stationary, fully developed, homogeneous, and axially symmetrical. We know this is not true in case of human body, because flow is not fully developed and is not stationary, has acceleration and deceleration phase, etc. But this is assumption. And I assumed that flow takes place in narrow tube, like for instance in aorta. In case of aorta, some researchers show that in a diameter of aorta is about 8.2 millimeters up to 9.3 millimeters, depending on organism. So I assumed in this case that narrow tube has inner diameter 8 millimeters. And I assumed that flow is transitional or turbulent. I will explain this later why I choose such assumptions. And bioliquid flow exhibits damping of turbulence. This is my hypothesis. I don't have a proof from literature, but this is my hypothesis that in case of blood flow, there is suppression of turbulence at the wall. Reason why I choose such assumption that bioliquid flow, like blood, exhibits damping of turbulence. As I mentioned before, some researchers just noted that erythrocytes, it means red blood cells, they migrate from the wall towards symmetry axis. And also some researchers noted that measured wall shear stress using magnetic resonance show that data are lower compared to CFD results modeling. And this reminds me some analogy of Wilson and Thomas hypothesis. Just in 1985, Wilson and Thomas proposed hypothesis that in case of kaolin's flow, there is suppression of turbulence at the wall, and as a result, there is a thicker viscous sublayer, and as a result, there is a lower friction than we expect it should be. So let's talk a little bit about rheology of blood. I collected data, experimental data of Wells and Merrills. He done experiments on blood for several concentration of red blood cells. I chosen two solid concentration of red blood cells, 43% and 70%. Blue lines are for 43% concentration of red blood cells in the blood, while the red lines show results for concentration equals 70%. The cycles points show experimental data, but while dashed lines show results of prediction using custom rheological models. If we consider non-Newtonianity in blood flow, we know there are several rheological models which predicts pretty fine this rheology, but in my case, I chosen custom rheological model, and the results you see on the screen, which are not bad. Considering mathematical model, we have to start from continuity equation and from the momentum equation. For the physical model defined earlier, the momentum equation is just in this form, as you can see. And also, in case of viscosity, instead of viscosity, we are using apparent viscosity. This apparent viscosity has got sense in the case when we expect there is yield shear stress. But blood possesses yield shear stress, and the yield shear stress depends on the concentration of red blood cells. So, concluding, using custom model, we can calculate that apparent viscosity can be calculated like it is at the bottom of the slide. And I used the Bosinek hypothesis, which is not seen here, I don't know why, but most important in the model is damping function, because I used London and Sharma turbulence model. This is two-equation turbulence model, which uses turbulent viscosity. And turbulent viscosity is calculated on the basis of kinetic energy of turbulence, dissipation rate of kinetic energy of turbulence. And there is also damping function, which we call wall damping function, or function of damping of turbulence at the pipe wall, etc. But this function is modified for the case when we expect that suppression of turbulence appears in such kind of suspension flow. So this function I proposed for solid particles, sometimes for kaolin flow sometimes ago, and this function possesses yield shear stress and the wall shear stress. So I used this function as well because I suggested hypothesis that in case of blood flow, there is suppression of turbulence at the Vern's wall. And also kinetic of energy of turbulence, epsilon, this is standard for London and Sharma turbulence model. What data I have used for simulation? So first of all, I made calculations for two cases. One case with solid concentration of red blood cells, 43%, and we see yield shear stress is 0.0325 of Pascal, and viscosity is also here, and blood density is also presented. Concentration of erythrocytes or red blood cells in the blood we call hematocrit. So for hematocrit 70%, you also see the data I have used. As I mentioned earlier, inner diameter was 8 millimeters, and the reason why I decided to make calculations for transitional and turbulent flow, while we expect that in case of blood flow in the human body, there is laminar flow. And this is true. Majority of flows in human body, those flows are laminar. However, if we assume that heart beats about 70 times per second, what is about average, and for each heartbeat, there is blood transported in amount of 70 milliliters per one heartbeat. So totally, there is 5 liters per minute transportation of blood in the organism. However, on the heavy exercises, this flow rate can be increased even by 5 times. So we can even expect 25 liters per minute in short time on the heavy exercises. So for this reason, you see there was 25 liters per minute transportation of blood, while in my calculations, I Maximum was 9 liters per minute blood transportation. I just arbitrarily decided that maximum Reynolds number I will consider is 5,000. This is arbitrary assumption. So for 5,000 of Reynolds number, there is a flow rate of blood 9 liters per second in case when concentration of red blood cells is 70%. You see this on the red lines. And the blue lines show results of wall shear stress for concentration 43%. You see that for 7.4 about liters per minute, the Reynolds number is also 5,000. And also I presented you data for water. We see that wall shear stress is higher for blood with higher concentration, which is not surprising for us because we expect it should be like that. And here is the lambda friction coefficient, which dependence of friction coefficient of flow rate. Again, friction is higher for higher concentration of red blood cells, which is not surprising as well. If we consider velocity distribution of this bioliquid, which is similar to blood, we see differences. If we will change concentration of red blood cells, there are differences in shape of velocity profiles. Why we are interested in velocity profiles? We are interested if you would like to consider heat transfer process. If we would like to calculate heat transfer process exactly, we have to have reliable velocity profiles. So we see that there is a change of velocity profile. I will say this in the conclusions. What is also important that in case of bioliquid similar to blood, the appearance viscosity is decreasing when wall shear stress is increasing. This is seen at the right side of this slide. But if we consider three different values of wall shear stress, the first equal 5 pascals, which correspond to laminar flow, and second 15 pascals, which correspond to transitional flow, and the next one 60 pascal, which corresponds to turbulent flow, we see that appearance viscosity is highest for wall shear stress equal 5 pascal. It means that yield shear stress is important. If wall shear stress is lower, it means in laminar flow is extremely important, wall shear stress, but seems to be less important in transitional flow and even less important in turbulent flow. So let's come to conclusions. There are several conclusions. The first of all, the Carson model, which was presented here, predict bioliquid rheology right. And second point, I would propose hypothesis that in human blood flow, there is decrease of friction at the aorta wall, which is due to migration of erythrocytes from the wall towards symmetry axis. And the influence of the yield shear stress on energy losses cannot be neglected if transitional or turbulent flow is considered. The increase of solid concentration from 43 up to 70% causes an increase in the wall shear stress of approximately 10% and 6% in respect to transitional or turbulent flow. If the yield shear stress increases, the velocity profiles have tendency to change shape from flat, which is due to turbulent, to more parabolical, which is due to laminar flow. In a future research, this is very important to focus what happens really at the aorta wall, how red blood cells are behavior at the wall. Do they immigrate? How it affects on the wall shear stress? I truly believe that this kind of research are important in near future. Thank you for your attention. have them.